Today's lecture is going to be on linear motion, which is chapter 3 in your textbook. We're going to go to the website Blackboard and go into the general physics course, and under the learning plans, unit 2, we will see the outline for chapter 3. This is the PowerPoint presentation in PDF format for this chapter. So looking at chapter 3, this lecture will help us to understand that motion is relative, that speed has a couple different forms, both average and instantaneous. We're going to be looking at the concepts of velocity, acceleration, and the conditions of free fall. Now, motion is relative. Motion of objects is always described as being relative to something. For example, when we walk on the road relative to the earth, but the earth is actually moving relative to the sun. So we always have to know what our frame of reference is and where we set our zero so that we can determine exactly, in this case, motion, what that value will be. So first, looking at probably the most relatable form of motion and just looking at speed. Speed is defined as the distance covered per the amount of travel time that it takes to go over that distance. The units for speed are going to be meters per second, and the equation to actually solve for speed is the amount of distance divided by that amount of time that it takes to cover that distance. So if a girl runs 4 meters in 2 seconds, her speed would be 2 meters per second. So we would put 4 meters on top and 2 seconds underneath. So 4 divided by 2 is 2, and then the units are meters per second. Now, average speed is when we look at something probably over a longer period of time, where we look at an entire distance covered divided by the entire amount of time that it took to get there. We take average speed many times when we're looking at maybe a distance traveled for a trip, for instance. Maybe we're going from Milwaukee to Green Bay. And we are going to, obviously change our speed periodically throughout that trip, but we can figure out on average, what the speed was that we actually went. So you would take that total distance covered divided by the total time interval. So here it says if you drive a distance of 200 kilometers in 2 hours, and your average speed then would be 100 kilometers per hour. So we would take the 200 kilometers divided by 2 hours, and then we would get the 100 kilometers per hour. So looking at a check your answer or check your neighbor type of a problem, we would say the average speed of driving 30 kilometers in 1 hour is the same as the average speed of 30 kilometers in a half hour, 30 kilometers in 2 hours, 60 kilometers in a half hour, or 60 kilometers in 2 hours. Well, the answer here would be D, 60 kilometers in 2 hours. If we take 60 and divide it by 2, we get 30 kilometers per hour. So they would be equivalent values. Now, the concept of instantaneous speed means, what is my speed at any given instant in time? Perfect example is when you're riding in a car and you look down at your speedometer and you see how fast you're going right then and there. That is an instantaneous speed. Now, velocity is basically speed with the addition of which direction we're moving. So velocity is said to be what we call a vector quantity. A vector quantity always needs 2 things to fully explain what it is. And in this case, velocity needs to be a magnitude, which will be the value of speed, and it also has to have a direction. So let's say I went 60 miles per hour, that would be my speed, but the addition of, but I drove it going to the north, makes it velocity, because now we have not only magnitude, but also direction. Now, speed and velocity sometimes are interchangeably used. And again, the only difference between them is velocity is the addition of a direction. Now, we say that speed is called a scalar quantity because it only needs one variable or one magnitude to fully define it. Velocity on the other hand is a vector quantity which requires two things, both magnitude, which is the speed, and a direction. Now, constant speed is something that we'll hear actually quite often in the next couple chapters. Constant speed or constant velocity means that we are going at a steady speed for a period of time. We're neither slowing up or we're neither speeding up or slowing down. Now, constant velocity has that same speed component to it. We're at a constant speed, we're staying at the same value, and we're staying in the same direction. If we turn a corner, for instance, if we go 90 kilometers per hour and we turn a corner, we are actually no longer going at a constant velocity because we've now changed our direction. So both quantities have to remain constant for us to be at a constant velocity. Now, acceleration was experienced and formulated by Galileo based on his experiments with inclined planes. He saw that the rate of velocity would change as he would observe balls rolling up and down inclined planes. Now, it might not seem like a big deal that as we roll down an incline, we're going to gain speed, or when we go up an incline, we're going to lose speed. But he saw that as the slope got larger and larger and larger, meaning more steep, the rate of acceleration would increase, or it means the rate of how fast those balls were going by the time they got down to the bottom also increased. So he observed that acceleration, that they were speeding up over time, and he was able to be the first scientist to really identify acceleration. Now, acceleration, as on this previous slide, is the rate at which velocity changes over time. So, velocity involves a change in speed, or a change in direction, or you can have both going on. Something about acceleration is that we can always feel it. We can always feel when we're slowing down. We can always feel when we're speeding up. So in a car, if we suddenly put on the brakes, we are going to physically move forward in our car. When we are speeding up, we're physically going to move back. But when we're going at a constant velocity, which means that we are neither speeding up nor slowing down or changing our direction, we actually don't even feel like we're actually moving at all. And so in this case, we have a car is making a turn. Even if that car would remain at the same speed going around that turn, because it's changing direction, it's accelerating. And we know that. We know if we turn a corner, we can physically feel it even if we're not speeding up or slowing down. So acceleration's equation is the change in velocity over how much time it takes to change that velocity. The units for acceleration are going to be the same units for velocity, meters per second, over the amount of time, which most often is seconds. We see acceleration written a lot as, in the metric system, meters per second squared. Now, an automobile is accelerating when? When it's slowing down to a stop, when it's rounding a corner at a steady speed, both of these or none of these. Now, the answer here is both of these, both of the above. So it's accelerating when it's slowing down. Now, sometimes you may hear of that referred to as deceleration. It's basically a negative acceleration. So we do say that it is accelerating, whether we're increasing our speed or decreasing our speed. So A and B are correct here, so C is the correct answer. Here's another one. Acceleration and velocity are actually the same. No. Rates, but for different quantities? Possibly. The same when the direction is not a factor? No, we know they're not the same. And D, the same when an object is freely falling. We know also that not to be true. So the answer here is B, rates but for different quantities. So acceleration and velocity are actually rates but of different quantities. So looking here at acceleration again, Galileo started to increase those inclines on those planes. So he noticed that the steeper, as I said earlier, the steeper the incline, the greater the accelerations. And as he approached and got closer and closer to straight up and down, which is what we consider a free fall, this would be without aided start and just dropping things on their own account, we would notice that we would have the greatest acceleration on the right here as a free fall, a vertical incline. Now, when air resistance was negligible, all objects fell with the same unchanging acceleration, meaning as long as the incline was the same slope going down in each case, it would continue to accelerate at the same rate. So free fall is falling under the influence of gravity only. Nothing else is helping it. So when we simply drop something, that is a condition of free fall. We also say that we do not worry about air resistance in the case of free fall. So freely falling objects fall to the earth and accelerate at a rate of 10 meters per second every second. Or we shorten that and we say 10 meters per second squared. Now, in this class, we will be using 10 meters per second squared for the case of just relating ourselves to the gravity. When more precise values need to be obtained, the actual rate of gravity is 9.8 meters per second squared. So I don't want anyone to think that when we see and we use the 10 meters per second squared, we are using it so that the calculations are easier. But in actuality, when we need precision, we will use 9.8 meters per second squared. So when we look at a freely falling object, we want to know how fast it's going. And we have a practice page that can help us with this. This is practice page number 8. It's green, in the green packet of practice pages that I gave you on the first day of school, and we're going to be looking at that in just a bit. Now, if we take the acceleration equation, we rearrange it, we can say that velocity is equal to acceleration times the rate of time. So under a free fall situation, when acceleration is 10 meters per second squared, the speed that we have going on after we drop something, we simply drop it. 1 second later, it's picking up 10 meters per second for every second. So 1 second later, we would determine that velocity of that falling object, and it would be at 10 meters per second. Another second later, still accelerating at 10 meters per second every second, that would mean that we are now going 20 meters per second. Then the next second that passes, we're going to pick up another 10 meters per second. So at 3 seconds, you're going to notice that we're going 30 meters per second. So the velocity at any given amount of time as we fall is going to be determined by the acceleration, in this case the acceleration of gravity, 10 meters per second squared, times the time it takes to get there. So in the case of 1 second, 2 seconds, 3 seconds, and so on. So using that philosophy or that concept, let's go to practice page number 8 from that green packet that you were given on the first day. And let's fill in all of the velocities on this page. So you'll notice here that we have an object that's being dropped. And we want to fill in, if there was a speedometer on here, we want to fill in the arrow for the actual rate of speed that it would be going at each one of the time intervals listed here. So you'll notice they drew in the first two for us. So at the very top at 0 seconds, we would be at 0 meters per second. Now, we drop it, and the only thing influencing it is gravity at 10 meters per second squared. I'm just going to turn the light on here. So you'll notice then as 1 second passes, if we're saying that gravity is only working on it, so that means that for every second that passes, we're going to pick up 10 meters per second. 1 second has passed, so you'll notice that the needle now is at 10 meters per second. Now now we go to 2 seconds. So we increase again, and it's picking up another 10 meters per second. So we do a plus 10 here. And now you're going to notice that the next number, the next notch here is going to be 20 meters per second. So our, our velocity here is going to be equal to the acceleration of gravity. Acceleration we're going to call gravity g, times the amount of time. So this is where we would take 10 times 2, and we would get 20 meters per second is the velocity at 2 seconds. Now we do it for 3 seconds. If we're at 20 here and we pick up another 10, we're going to be at 30. Then for 4 seconds, you see the pattern, it's going to be 40. Then at 5 seconds, 50. And at 6 seconds, we're going to be at 60. Okay? So those are the values of the velocities as it goes down. So the higher, the longer it's in the air as it drops, the faster it's going to continue to go, picking up 10 meters per second every second. So for number 1 here, we can say the speedometer reading increases the same amount of 10 meters per second each second. This increase in speed per second is called acceleration or gravity. Okay? So we'll go back to fill in the other values in just a bit when we talk about how distance is related. Okay. So, a check your neighbor question. Free falling object has a speed of 30 meters per second at 1 instant. Exactly 1 second later, its speed will not be the same because it's freely falling. It's acted on by gravity. And after each second passes, we're going to add another 10 meters per second. So in this case, it won't be the same. It won't be 35 because we need to actually add 10, right? It will be more than 35, but it won't be 60. So our answer here is 30, with the actual value being 40 meters per second after 1 second passes. Now, when we're in a free fall situation, not only do we want to know how fast something's going, but we want to know how far it goes. And the equation for how far is going to be a distance. Distance is equal to 1/2 the acceleration that something is experiencing times the time squared. Okay? So if you want to see the derivation of this, it's on the bottom of on the bottom of the free falling section in your book, where it talks about how to develop that. It was done in the video, so I'm not going to take time here, but the equation that we're going to use is 1/2 the acceleration times the time squared. So in a free fall situation, the acceleration is equal to gravity. So we would say that the acceleration is equal to 10 times 1/2 is 5 times the time squared. That's one way to kind of use it and have it as a little bit easier value to actually calculate in your head. So if we go back to our green sheet, page 8, we'll notice that on these speedometers, there's a place for the distance, or if we would take it as an odometer portion of this speedometer. So you'll notice here at 0 seconds, the distance traveled is obviously 0. Now, 1 second later, we want to determine how far did it fall after 1 second. So using that distance equation, 1/2 times g times t, which we can shorten up, and we can even say, knowing that g is equal to 10, we can multiply it by 1/2. We can say 5 times t squared, which is convenient for figuring these out. Now again, remember, this is an estimation. This is not actual value. If we wanted to know exactly the distance, we would be using the gravity equal to 9.8. But we're going to continue to use 10 here to really get the idea and be able to correlate this. So you'll notice that if we have 1 second has passed, our distance is going to be equal to 5 times t squared. So our t is 1 second. So 1 squared is 1 times 5. Our distance is going to be equal to 5 meters. So that's what they put here, 5. The next one is 2 seconds. So here my distance is going to be equal to 5 times t squared again. So this is going to be 5 times 2 squared. So 2 squared is 4 times 5 is 20. So d is equal to 20 meters here. So we're going to put 0 to 0. Then we're going to do the same thing for 3 seconds. D here is equal to 5 times t squared. So we're going to take equal to 5 times 3 squared. So 3 times 3 is 9, times 5 is 45 meters. So 0, 4, 5 here. The next one that we have is 4 seconds. So d is equal to 5 times 4 squared. So d here is going to be equal to 80 meters. Then we have d is equal to 5 times 5 squared. So this is 25 times 5 is 125 meters. And then lastly, we have 5 times 6 squared. So 36 times 5 is 180 meters. Now, finishing up this part of the page, we can say the distance fallen increases as the square of the time. And then if it takes 7 seconds to reach the ground, then its speed will be at an impact will be, well, we know that speed is acceleration times time, so 7 times 10 is 70 meters per second. And the distance fallen is going to be d is equal to 5 times t squared, so 49, right? 7 times 7 is 49 times 5 is 245. And its acceleration of fall just before impact will be the same as it was when it started. Still going to be the acceleration of gravity for that free fall, 10 meters per second squared. So, what is the distance covered of a free falling object starting from rest after 4 seconds? We know that to be 5 times t squared. So that's going to be 4 squared. This is going to be our time, times 10. And so, I'm sorry, times 5. So we're going to be at 80 meters for 4 seconds. Sure enough, 80 meters. Okay, now in our book, I want to look at an example or two that expands on these ideas. Figure 3.8 in your book, and I'm going to peek back over here and look at this illustration in our book. We're going to notice that we have a man standing on a ledge, and he is throwing an object up, so throwing a ball up. And when it initially leaves his hand, it is going to be going at a rate of 30 meters per second. And the direction it's going to be going is going to be going up, okay? So its velocity is going up at that point. Now, we know that a ball is going to continue to go up until it gets to its highest point and then going to start coming back down again. Now, when it's in the air and it leaves his hand, after each second, it is still going to be acted upon by gravity. Now, we know that gravity always pulls things down. So, after each second here, if this goes up and it has a value of, let's say, the 30 meters per second, but after 1 second, it's acted upon by 10 meters per second of gravity, 10 meters per second squared of gravity. So if we have 30 going up and we have 10 coming down, do you see how it slows down by 10 after each second? And now at 2 seconds, or after 1 second in the air, it's going to be at 20 meters per second. And then after another second in the air, it's going to lose another 10, because if it's at 20 here, 10 is going to act on it still to slow it down, and the difference here is going to be 10 meters per second until it gets all the way up to the top and it loses that last 10 at a value of 3 seconds. So notice here that when I throw it up with 30 meters per second, it's going to take 3 seconds to lose its velocity, and that's when it's at the top of its trajectory. Here the velocity is equal to 0. Now, As it's at that point, it's changing direction, right? So now it's going to start coming down. And as it goes down 1 second later, or at the 4-second mark that it's in the air, it will be going at a velocity of negative 10 meters per second. This negative simply means that it's going down. Now, this is our speedometer problem that we had. This is our green sheet where we started at 0 and we now are down 1 second later and we're going 10 meters per second in a downward direction. Now, after another second, when we get to 5 seconds in the air, or the second from when we are down from the top, we are going to be going 20 meters per second going down. And again, the negative means down. And then after another second, we'll be going 30. Notice this is that same level. It's coming back down. It's going to be at that same time, that same meters per second, but opposite direction. And if it continues to fall, if it doesn't stop here, but it continues and it's going to go past the ledge, after another second, it's going to pick up a little bit more speed and it's going to gain another 10 and it'll be going then a negative 40 meters per second. Okay, so that is something you're going to find to be useful for you when you start doing your application problems for Unit 2. So that really concludes Chapter 3 here from the book, the outline from the book. I encourage you to take time to read this in its entirety. The author does a great job of explaining each one of the sections. So do indeed do that as you study and you look forward to the quiz and doing your application problems.